Hello, my name is Karlo Jukic, and this is Lab 3. For introduction, the purpose of this lab is to understand magnetic fields through a code simulation and determine a relationship between distance and a magnetic field, as well as using the Biot-Savart law to find the magnetic moment of a magnet. Fundamental theories here are the Biot-Savart law, which you can see the two versions listed above, the normal version and then the linearized version, which we'll use in the graph later, and our distance relating to a bar magnet. For our result previews, our n is equal to negative 2.263, and our dipole moment was 10.62. For our models and assumptions, our assumption is that this bar magnet will act as a magnetic dipole, which you can see kind of displayed here. And our system will be the bar magnet, and our surroundings will be everything else in the experiment. For our experiment setup, we have a phone with a magnometer app set up. We'll orient the phone orthogonal to the Earth's magnetic field and determine the location of the magnometer chip on the phone while the bar magnet is on the end of the ruler. This is done with tape, as you can see in the diagram on the right, marked with two strips, and after using both axes, y and x on the meter to determine this. The on-axis distance from the bar magnet from the meter was then measured and linearized, and these values were used for calculations will be coming in the following section. Here it is. Pause it if you want to look at it. The off-axis field procedure is like the previous on-axis one, but instead was moved on a perpendicular distance and measured, and we can see the data below also from the experiment. For our calculations, we're using the experimental data. Needing calculations, we're using the formulas in the previous introductory section. Here we found that our K is 2.124 e to negative 6, and then the end our moment was 10.62 amps times meter squared. Here we'll have our GLOSUP code. We'll start with defining our constant, and then defining our magnet object and plugging in our mu mag that we found earlier. Then we'll create a function for a magnetic field using standard equations that we saw in the introduction. Then some arrow scaling, setting our observation distances equal to our distances and our negative distances likewise in the line 55 downwards. And then we will draw two arrows to make a magnetic field for this on-axis portion. This will then go into making magnetic fields perpendicular to display these objects, and then also making an off-axis model, printing all our values, and then being done. Here we see how the model ran. And comparing it to our real data, we actually got some very different values. Starting mainly looking at the BFD45, we got some pretty different. We got a different distance. We got a different BX, BY, and a BZ, which is still should be negligible because it wasn't being measured or oriented in this lab. But definitely some variations. Potential errors and assumptions is some assumptions are that this bar magnet acted exactly like a dipole, and that the magnetic field will decrease with respect to distance. These are both assumed, so these could be either slightly different or have more aspects to them. Some errors could be that other electrical items interfere with the data in the meter, as we were doing this in the lab with a lot of computers around that we couldn't really get rid of, so that might have hindered it, as well as human error in placing the magnetic chip in distance. Observations, marking going down by true, false, false, true. Was true is that the magnometer is far away. It measures a near zero magnetic field in the x direction. That's true. What's false is that as the magnometer moves close to the magnet, the measured x component of the magnetic field decreases, and that the position of the manometer has no effect on the measured x component of the magnetic field. It's both completely false in the experiment. Another true one was that the magnometer moves close to the magnet, the measured x component of the magnetic field does increase. For our what ifs, we have a what if you hadn't oriented your experiment to compensate for magnetic north and instead laid the stick at some intermediate angle. And this would result in the Earth's magnetic field interfering and skewing our results to a varying degree depending how badly we skewed and put our angle on the trying to compensate for the field. And our what if you were to stick two identical magnets together end to end and run the experiment, and that would just be the field's magnitude would double but stay in the same direction. Thank you for watching.